All right, hey guys, and welcome. We've now gotten through chapter 2. Just gonna have to assess it, see how we did, and 2 out of 11 chapters in the book. You're doing pretty well. So at this point in the book, what I usually like to say is you probably know something, right? You know something about geometry. Hopefully, you know a little bit more than something. But what I'm trying to get at is you came in at the beginning of this year, and what I like to say, what I'd like to feel like maybe when you started this was, hey, maybe I knew nothing. I really didn't know much. So you're seeing this unfold. It's kind of coming together with some of the initial definitions and postulates and theorems that are going to set the stage for everything else you're going to prove and do, and those facts you'll come up with about how we measure the world around us. Okay, so at this point, does it feel like you should know everything? Does it feel like you should be perfect at all of this? Well, no, but you shouldn't know nothing. You should know something at this point. So anyways, we're going to get into it in a minute. Before we actually get into the chapter test, the chapter 2 test, which is the practice test I have a little bit later on here, before you do that, before you jump into studying, my recommendation would be actually to check out this chapter summary. This is on page 99. On page 99, we have these 9 things that you should have learned this chapter, and just quickly review it, okay? So quickly read through this. Yes, I know what parallel lines are. I know what skew lines are. I know what alternate interior angles and corresponding angles are. I know what happens when parallel lines get cut by a transversal, okay? So just read through all this. I'm not going to go through all of this with you because all of this should seem pretty obvious by now. If you've been doing the homeworks, if you've been reviewing in class, all of this should be kind of reviews, right? At any rate, any triangle, for instance, the sum of all of the interior angles would add up to 180, right? That should be a fact that you know because we proved that one. We've practiced it in various kind of algebraic problems and other problems like that, okay? Also, too, the sum of the interior angles of any convex polygon, right? Lots of words, but you should know that that is the product of 2 less than the number of sides that polygon has times 180 and whatnot. Okay, so just read through all of this and decide, is there something you need to look at? Is there something you need to refresh on? Because this is what you're going to be assessed on, and this is what you want to practice and really, really study. So that being said, read through this, think about how you're going to study, and then we'll jump into the chapter 2 practice test and do some problems together. Or you can just check your answers afterwards. But anyways, that's the idea. Let's get into it now. All right, and here we are. Let's do this. Chapter 2 practice test. We got it right here. This is on page, let me check what page this is on. So page 99 was the review page. Chapter test is on page 101. Okay, so you're going to want to have page 101 up here. Let me write that down. So you'll find this chapter test on page 101, and yeah, you'll do this test. This will give you a good background into kind of your assessment. I usually say this is maybe slightly a little bit easier, perhaps, than a formal assessment, because again, geometry, there are a lot of topics, right? There's a lot of definitions, theorems, postulates, in addition to all the algebra kind of problems you have kind of in here. So there's only so much we can test you on. There's only so much that you can kind of prepare for in one chapter test. So because of this, right? This is something that I repeat with my own students quite a bit. Your study guide isn't actually just doing this chapter test and reading this. That's probably not enough. It's also studying your homework, okay? Your homework is your best guide to study for a particular test, because those are the problems we know that all of us have been practicing with one another. So I usually recommend taking a look at the A-level problems, right? Those should be pretty easy for you going into a test. But really kind of the B-level problems, those are going to kind of represent kind of like what some of the slightly harder problems there are, okay? Usually C-level problems, those are usually at least a little bit too hard, a little bit too time-consuming to appear on an assessment in class. So really, I really focus down. If you don't know how to do a B-level problem, if it's not the night before the quiz or before the assessment, try to get in contact with your teacher. Get in contact with a peer if it's the night before a test. Try to get help and really try to work your way through that struggle and kind of your understanding with problems ahead of time, and then you'll be in good shape. Okay, so just a reminder here, this is a good review, I think, by doing this chapter test, but it's not everything, right? It's very hard to prepare for a test at the exact level you need to prepare for, an exact level of difficulty, for instance. So I think these problems are a little bit easier, maybe, than they could be. So that's why maybe you're going to want to look at your homework too. Okay. That being said, let's get into it. Let's go jump into the chapter test. So at least we can go through a bunch of problems, and then you can see the solutions, and you can kind of get a sense of where you stand as you continue studying for this. Okay. Chat page 101. Let's do this chapter test here. All right, we're looking at number 1. Let's start with number 1 right here. It says complete each statement with the word always, sometimes, or never. Ooh, it's these classic problems. Always, sometimes, or never. Okay, so remember when you have a theorem, for instance, right, that's something that's always true. A theorem that is something that we know is always true. For instance, if you have two parallel lines cut by a transversal, right, if you have that, if that's your hypothesis of your theorem, then you're going to know the conclusion has to be true. Then, for instance, alternate interior angles would always be congruent, right, if you had parallel lines, okay? So if you have a theorem is a statement of pure truth. It's always true. We know it to be true because based on our basic assumptions and definitions, we know that things logically follow from it, okay? So that's one thing to look at when you're doing always, sometimes, never problems. Is it a theorem? If so, it's always. Sometimes, right? Sometimes is something where you can think of, okay? So always true, we can kind of think of that as being kind of theorems or other postulates that we know are definitely true. I'm going to put theorems, postulates, that's what we're looking for here. Sometimes we're looking for if we can figure out an example, right? An example of it being true, then it's either going to be sometimes or always. But for the difference between sometimes and always is that you can think of examples of it being true, but you can also think of something called counterexamples. Okay, so I want to put that in front of you here, and hopefully that has been kind of defined for you right here. I think there's only one R in counterexamples. Counterexamples are, given a premise, right? Can you think of a situation where it would make the conclusion not true? So for instance, if I were to say, if two lines were cut by a transversal, then alternate interior angles are congruent. Well, that could be true. And when is it going to be true? Well, it would be true if those two lines are parallel, okay, so that's sometimes true, but it's not always true because it's possible to have two lines that are not actually parallel. For instance, these two lines are not parallel to one another. They're going to cross at some point. So a transversal that would go across those two lines, this angle is not congruent to that angle right there, right? This is an acute angle, that's an obtuse angle, even though they're alternate interior angles, okay? So that would be an example of a statement that would be sometimes true, because I can think of examples, right? When two lines are cut by a transversal, they could have congruent alternate interior angles. It would require those two lines to be parallel. But I can also think of a counterexample, in a situation where that statement would not be true, which would be a counterexample right here. Two lines cut by a transversal where alternate interior angles are definitely not congruent. This is not congruent to that, okay? And then you can think of never true, okay? Never true are just statements that are, you can't think of no true examples, right? No true examples. So it's only counterexamples, really. So that being said, let's see if this helps out with number 1 right here, okay? Number 1 says that two lines have no points in common are blank parallel, okay? Two lines that have no points in common are blank parallel. Well, we know that two lines that are parallel would have no points in common. So we can think of an example. Can we think of a counterexample of two lines that have no points in common that are not parallel to one another? Well, we might have to go to 3 dimensions for this, okay? So I'm going to draw a cube out here real quick. And a cube holds you the key to thinking about how lines relate to one another in 3-dimensional space. And let me drop this in here and finish up the cube. A cube is going to demonstrate for us that we can come up with some other lines that are not necessarily parallel to one another, but actually do not intersect. So for instance, if I draw this line right here that's on this edge of the cube, and I draw this line right here that's on this edge of the cube, if I drew this exactly perfectly right here, in fact, actually, you can pretty much see that if this were flat right here and this were completely vertical, and they're located in different places right here in space, then these would not actually intersect here. So these would be two lines that have no points in common. So these are two lines that exist in space here that have no points in common. And they're not parallel. This doesn't fit the definition of being parallel, because definition of parallel, right, needs to be one, coplanar. Two lines need to be coplanar. And 2, they don't intersect. So what this statement here is neglecting are two lines that have no points in common that are not coplanar. And these lines, what are these lines called again? Can you guys remember what these lines are called? So if I draw this, they don't intersect, they're not parallel, then it would be skew. So this would be sometimes. Sometimes right here. Ignore what I write down. The answer is sometimes. All right, number two, let's go to number two here. If a line is perpendicular to one of two parallel lines, then is blank also perpendicular to the other one? So let's at least try to come up with an example of this being true. And I'm actually going to steal that cube that we had up top here. So an example of this being true is if we have these lines are obviously parallel to one another. These two edges, the lines that contain the edges of this cube here on opposite sides of this front face of the cube, these are obviously parallel to one another. And this line right here, if I drew this line, this is, since it's a cube, well, we haven't defined cubes yet, but cubes are made up of 6 congruent squares. So this would have to be a right angle right here. So it's perpendicular to this line and perpendicular to this line. So if this, this would be an example of, yes, this being true for at least this one instance. If a line is perpendicular to one of two parallel lines, so it's perpendicular to this one, it's perpendicular to that line too. So that one's true. But can we think of a counterexample? And here I drew my cube. I would like to see, if you're in my class, I would like to see on assessments you guys drawing out the cube. I think that's good. I think it's a helpful trick to do to get this, okay? Let's think about this here. So let's deal with the same two parallel lines right here. Can we draw another line that's perpendicular at least, to this one that is not actually perpendicular to this one? Yeah, we could draw this in right here, right? We can draw, well, like this line here. That would be part of, we got to get some depth going here, so let's do this. Part of going backwards and going to the side. This line on this face here would be perpendicular because this side of the cube, on this side on the face on kind of the side of this cube here, not the front of it, it would be perpendicular because it's a square here. Okay, so this would be perpendicular to this line. But would it be perpendicular to this line that's parallel to this edge of the cube? No, right? It's not perpendicular. In fact, it doesn't even intersect this, so it can't be perpendicular. So here's your counterexample here. It's possible for a line to be perpendicular to one of the parallel lines, but then be skewed to the other one of the parallel lines, okay? So this is where it should have said, if a line in a plane is perpendicular to one of two parallel lines in the same plane, right, then it would have to be perpendicular to the other one. So this is a common thing. You're thinking about, are you writing rules for the plane, or are you writing the rules for the space? And the way that this is written out is that way that this is written out is that it's written for space, and this, it can either be true or cannot be true. So this is sometimes. Did I write never up top here? I totally shouldn't have wrote never up top here. This is definitely sometimes up top, okay? Two lines can have no points in common. They can be parallel or they can be skewed. So this should have been sometimes. Sorry about that, guys. Thought I made that clear when I explained, so I'm gonna leave this in here, okay? So we got sometimes for the first two of these, okay? Moving on to number 3. If two lines are cut by a transversal and same side interior angles are complementary, then the lines are blank parallel. Think about it for a second. Well, I think on this one, it might be easier to start with a counterexample first, because this is clearly wrong here because this is not used to the way that we're used to seeing this. It says if two lines are cut by a transversal, right? If those lines were parallel, those same side interior angles, they wouldn't be complementary. They'd be what? Well, let's check it out here. So let's do two parallel lines, and then we cut by a transversal. These two same side interior angles wouldn't be complementary because, in fact, right, one of these, or unless they're both right angles, one of these would have to be obtuse to begin with, okay? If you're obtuse, you can't be complementary with another angle because you're already over 90 degrees. So these are supplementary, okay? Not complementary, supplementary. So if we have two parallel lines cut by a transversal, they're gonna be supplementary. They're not gonna be complementary, okay? So in this case, we can't actually come up with two lines and then draw, right? We could draw the transversal like this, like this, like this. And, right, let's do this, two 90-degree angles, right? Obviously not complementary, they're supplementary, okay? So there is no example, but there is a counterexample. So because of this, only counterexamples, we're gonna put never up here. Never up here, okay? So to summarize so far, if we have examples and counterexamples, it's sometimes. And here we had an example, we had a counterexample, so this is sometimes. Only counterexamples, it's gonna be never. Right? And if it's something that's written like a theorem, that's just the conclusion's false, right? Misleading here. Notice here the hypothesis is fine, right? If two lines are cut by, or two lines are cut by transversal and same side interior angles, right? If we knew that they were supplementary, then the lines would be parallel, but not if they're complementary. They're not going to be parallel there. An obtuse angle is blank a right triangle. Well, here's just testing you. Do you know what a right triangle is? A right triangle is, and do you know what an obtuse triangle is defined as, right? So an obtuse triangle is defined as the measurement of the largest angle. So I'll just put measurement and angle. You'd have one measurement, right? So at least one, but obviously you're just going to have one. That's the most you can have in a triangle. The measurement of the angle is greater than 90. And what's the definition of a right triangle? Oh, you'd have one of your largest, right? Your largest angle is going to measure exactly 90 degrees here. Okay, so these are mutually exclusive. You can't be one and then also be the other. Okay, because 90 is less than numbers greater than 90, for instance. Okay, so here you'd only have counterexamples. So you're going to put never right here. Obtuse is distinct from right. In triangle ABC, if AB is perpendicular to BC, then AC is blank perpendicular to BC. Well, this is sort of getting at what I was saying a second ago. We're dealing with a triangle ABC, and if we have this here, and I'll draw it in the counterexample area because I already know the answer to this, right? If we had triangle A, B, C, and we have a right angle at B, right? It would have to be right angle here if this is AB perpendicular to BC. So that would mean that angle B, by definition of perpendicular, is a right angle. And we can only have one right angle in a right triangle. That's the only way possible, right? In a triangle, you only have one right angle. That's the maximum. Because if you had, say, this is the side of a triangle, and you had a right angle here, there's no way to connect this side to this vertex, for instance, right? You just have two parallel lines, and that's not a triangle. So we can't think of any examples. We can only think of counterexamples, right? And that would be this is really where we have our counterexample over here. That if you have two right angles here, because AB perpendicular to BC, then there's no way that AC, right? AC could be perpendicular. It's going to be acute, right? Going to be acute. Okay, so it's only counterexamples, not examples. Then this is going to be never. I'm waiting for an always. We haven't had an always yet. We're due for an always. This is another way to take tests, is that sometimes there are patterns here. If they're giving you all the same thing, maybe at some point they'll give you an always thing. Okay, and I hope I got these right too. I'll check my answers later. As the number of sides in a regular polygon increases, the measure of each exterior angle decreases. Ooh, I like this one. Okay, so here's the one where you're trying to get the measure of each exterior angle. Here's one where you just kind of have to memorize this formula, I'm kind of hoping. And so the measure of the exterior angle, okay, measure of an exterior angle is, the formula you use for that is 360. Remember, the exterior angles of any polygon, right? Any convex polygon, regular polygon would be convex. So any regular polygon or any convex polygon, that is, sums to 360. Okay, 360. So the more sides it has, the smaller those exterior angles are going to be. So 360 divided by n. So picture like a square, for instance. This helps you remember that the exterior angles, remember, exterior angles just go in one direction if you just extend it out. So you'd have this 1, 2, 3, and 4. These would all be 90-degree angles, right? 90-degree angles for a regular fourgon, right? This would be a regular four-sided figure, which is a square. And they would all be 90 degrees. So if we add on sides, right, if we tack on sides right there, so what if we had a pentagon, a regular pentagon, then those exterior angles, right, having diagrams down on tests and assessments are really helpful to show that you're thinking, show me that you're thinking, and also show yourself that you're thinking here. These angles are going to be smaller. Notice that they're acute, right? They're acute right here. Okay, so this is another reminder, right? They're going to have to be acute because your interior angle is 108. For a pentagon. If you don't have that memorized yet, you'll get there, right? You'll get practice on problems. You'll see that 108 number come back. Oh, yes, you will. So these are all 72 degrees, okay, which is less than 90 degrees for a circle. For a square. So 360 divided by n. So the more and more as n increases, right? If this is increasing, then the actual, if n increases, the number of sides increases, then the actual exterior angle, like for instance, it's 72 over here, it decreases. All right, so we can only think of examples where this is true, right? If we add up more sides versus a hexagon, it would be a 60 degree, a regular hexagon is 60 degree exterior angle. So this one is, oh, we can only think of examples of it being true. So this one is always. All right, and finally, for our always, sometimes, never fun. And I say fun, right? Because these are just really thinking problems. I think through them. Right? Don't go too quickly on them, and then you won't like them. Like a lot of people don't like them. The converse of a true if-then statement is blank true. Well, hey, let's at least start with the one that I keep saying here, which is, and we'll tuck this into the examples column right here. If two parallel lines. All right, if we have this as a theorem, right? So this is a true if-then statement, right? It's a theorem. If two parallel lines are cut by a transversal, then their alternate interior angles of that whole line relationship, they're going to be congruent, okay? We know that's true because it's a theorem, right? It's a proven fact. And it's converse, right? I say this one a lot because its converse actually is also true, right? So you're going to have some examples of this. So this one was always because we only had examples. So this could be either always or sometimes, but the question is, are we going to have counterexamples in a second? So just to give you a sense of why do I know the converse is true? Well, if two parallel lines are cut by a transversal, then their alternate interior angles are congruent, right? If we flip, right? If we flip after the if, we have our hypothesis, two parallel lines cut by a transversal, and then after the then, we have our conclusion. If we rearrange that so that it has the structure of a converse, right? We're just flipping where our hypothesis is and our conclusion is. And you'll notice that's going to return us a true statement. It'll be also another true geometric, scientific fact, what have you, okay? So if alternate, right, interior angles, and in order to have alternate interior angles, you'd have of two lines, and we don't know they're parallel, are cut by a transversal, then our hypothesis here was that those two lines were parallel, so that should be the conclusion here, okay? So our cut by transversal, then lines are parallel. And we know because we've proven this one here that this is absolutely true, right? If you had alternate interior angles when you had two lines cut by a transversal, then the lines were indeed parallel. That is true. The original statement was true, so we know that the converse of a true if-then statement is sometimes true. The question is it always true, or can we think of any counterexamples, right? Can we think of any counterexamples here? I had to look at the textbook for a second because I was really thinking through this, but I know the answer here is going to be sometimes, so let's at least put sometimes here because I found a counterexample. And that's this theorem here, this corollary right here. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So let me write that down here. So this would be an example of a true if-then statement, right? Given the hypothesis that we have two angles of one triangle congruent to two angles of another triangle. I didn't write that in. Then the third angles would be congruent also, right? Because those two congruent triangles would add up to the same sum of their measurements in both triangles. And then you take that away from 180, that means that the third and only last angle that's in both triangles would have to be the same. It would just be the remainder of the sum of the other angles of the triangles. Those remainders would be the same because you'd be subtracting the same out of 180, okay? So the converse of this is not going to be true, right? The converse of this is we take the conclusion, right? And the conclusion here, the third angle is being congruent also. That becomes the hypothesis. So we're talking about third angles. We're talking about just one angle in both triangles. And if we knew and this, the converse is obviously not true. Terrible handwriting right here. It's hard for me to write this in. But the converse would be this, right? If an angle in one triangle is congruent to the angle in another triangle, then the other two angles would be in that one triangle would be congruent to the other two angles of the other triangle. And that's totally not true, right? If we have two triangles, and for instance, we have a 60-degree angle in this triangle, and we have a 60-degree angle in this triangle, we would know that, for instance, these two angles here, right, aren't going to be the same and necessarily the same as these ones. For instance, I tried to draw this like an equilateral triangle. This could be 60 and this could be 60. And notice here that this is much more acute than that 60-degree angle. So it's possible that this is 30 and this is 90. Okay, so this is a situation where if we know that these two angles were the same as these two angles, then the third angles would have to be congruent. That's the theorem. The converse of that theorem, not true, right? If we know that this third angle right here, these two angles congruent to one another, we're not going to know that these two angles are actually congruent to those two angles. 30-60 here adds up to 120, so does 16-60. Okay, there's not much more we know beyond that other than what they sum to. Okay, so that's always, sometimes, never right there. An example, we can think of only examples. And we thought of a counterexample, yes, the counterexample where it was not true, and that's this is our counterexample. Then our answer here is sometimes. The converse of a true if-then statement is only sometimes true, right? If it's always true, then the if and only if statements, we'd be using that all the time, okay? So 6 always, and I hope I got these all right. I'll check my answers afterwards. Okay, jumping into more kind of algebraic stuff. Find the value of x, measure angle 1, equals 3x minus 20, and we also have measure of angle 2 equals x. So here's where it's practicing notation. You know that m means measure of angle 1, and we're allowed to set up an equals sign there because it says measure of. And yeah, we have x and variables, so you're probably going to have to do some algebraic solving on this one. And you also have knowing notation here that you know what to look out for this, which I didn't do in all of these here. Did I do any parallel lines where I didn't show this? Let's see here. I put parallel lines there. Yeah, this is didn't get that to work out. I think I showed parallel lines on a lot of these. Didn't show parallel lines here. I should have showed that. Okay, so if you have kind of these arrows kind of in the middle of the lines, not at the ends here. If you have the arrows at the end, that kind of means it goes on forever. But if you have a pair of arrows in the middle of the line, right, that just means they're parallel to one another. Okay, so we have two parallel lines, and they're cut by a transversal, right? This would be a transversal. It would be intersecting both of the lines, and it'd be in the same plane as both of those lines. Okay, so here we have measure of angle 1 is 3x minus 20, and measure of angle 2 equals x. Okay, so these, we don't really have a great name for both of these, but we would know. So when you have a problem like this in the test, first thing you do, you mark it up. What do you know? Okay, so measure of angle 2, that's going to have to be congruent to, or the angle 2 is going to have to be congruent to angle 3, or the measures would have to be equal to one another. And then because we know that this is a linear pair right here, or this is a straight angle, right? 1 plus 3 would equal 180, okay? If these are the same then, right? If measure of angle 1 plus measure of angle 3 equals 180, and 3 equals 2, then that would mean measure of angle 1 plus measure of angle 2 would have to equal 180. So that's what we'll do in this one. Measure of angle 1 plus measure of angle 2 equals 180. So you set up your relationship based on what you can conclude. How do they relate in terms of numbers or equality? And these don't equal each other, but we know that they add to 180 because 1 and 3 add to 180, and 2 equals 3, right? Measure of angle 2 equals measure of angle 3. So now we can just replace this with the expression that represents what angle 1 must measure. So this is getting you to practice your algebra 1 skills. 3x minus 20, and then for measure of angle 2, we're going to replace that with x, and then we're just going to simplify and solve. Combine like terms, 3x plus x is 4x. Minus 20 here, we could add to the other side now, but I'm just going to move it around so we can go a little more slowly in this video. And I'm going to add 20 to both sides now, so I combine like terms. Then I'm going to use the addition property of equality to help me simplify here. So again, I start away from x. You don't want to deal with x yet. You want to deal with getting rid of the constant. So you simplify and solve, right? And you should remember this from Algebra 1 by starting away from x. What's away from x? What's one thing I can simplify to make my life easier? And that's getting rid of this negative 20. So I get rid of that by adding 20 to that side and adding 20 to this side. And then we would know that 4x would have to equal 180 plus 20 is 200. So 4x equals 200. And then last step, if we know 4x is equal to 200, what do 1x need to represent here, okay? Division property of equality, that's what you do in this one. You'd flex that division property of equality, and then you'd get 50. So x equals 50 in this problem. Pretty easy problem. This should be a pretty easy problem on an assessment. They get harder, right? They get harder. Look at the B-level problems and seek out help on those if you need help. Question number 9 here. Let's see if this is a little bit harder. Measure of angle 2 equals measure of angle 3. So these you just set equal to each other and solve. That's it, right? Measure of angle 2 and measure of angle 3, you should know the names of these. They correspond. They're in the same spot, right? They're kind of, if you have 1, 2, 3, 4, right? They're all in position 4, kind of 1, 2, 3, 4. Anyways, they're in the same spot, so we say they're corresponding. And they're corresponding angles where you have parallel lines cut by a transversal. So we know that this relationship, measure of angle 2 equals measure of angle 3, must be true because it fits that theorem that when two lines are cut by a transversal, two parallel lines, that is, you needed that in your premise, cut by a transversal, then corresponding angles are congruent. So let's set it on up. Okay, a few different ways you can solve here. Hey, you got a 4 factor here. 4 is not a factor of this. Actually, I won't divide both sides by 4. I'll distribute. Okay, so I'll distribute to solve this. Again, practicing your Algebra 1 solving skills. So, right, solving by rewriting here, you can do 2x plus 12, rewriting the right side just to make your life a little bit easier. Then you get 4x minus 28. And then we're flexing our Algebra 1 skills here, right? We got to collect our variables to the side that has more of them, right, to keep our variables positive. So I'll subtract 2x from both sides of equals, right? Subtraction property of equality. And then I'll also move my numbers, my constants, over to the other side. So I'll add 28 over here, and I'll add 28 over here, addition property of equality, using those both properties of equality just in one step. And so I've eliminated the amount of x's here. Now I got 2 x's on the right side. What do I have? I've eliminated this negative 28 by adding 28 to the side. So now I don't have 12 anymore. I got 28 more than that, and that's 40. So this was also a pretty easy problem right here. So our solution for x is that x is going to equal 20. All right, well, Reuben, let's keep going here. Let's keep going. Find the measures of the number of angles. All right, let's do this. Find the measure of the number of angles. X, Y, Z is regular. Oh, heck yeah. Regular figure, okay? So that's a regular 3-sided figure if they're giving you 3 vertices. So we know that that's going to have to be a triangle, right? Triangle. We have an equilateral triangle right here. Very nice. So an equilateral triangle is also equiangular. Right? Remember that corollary? So these are all 60 degrees. And if this is 60 degrees, well, I don't even need to actually put the 60 here to determine that the 3 is going to be 120, because we could use the exterior angle theorem to just add the 2 remote interior angles together to figure out angle 3 is 120 degrees. Okay, so, right, you could obviously, if this would have to be 60 because it's equiangular, and this is supplementary, but if this is supplementary to that, and these 2 are supplementary to that, you can just add these 2 together to figure out what the exterior angle is here. So that's 120. Okay, we got those 3 done. Let's keep going here. 11. Easy problem here. Let's see if this one looks a little bit harder. A lot more to kind of digest and take in and solve in this one here. All right, what do we know about this symbol? What does this mean again? This is a 90-degree angle. So we have a triangle. We know 2 of the angle measurements of the triangle. Are we going to know the third? Well, we know that they add to 180. So 180 is going to equal measure of angle 1 plus 90 plus 32. So we can also, if you want to do it faster in your head, rather than kind of do the algebra out over here, you can also remember that if this is a right triangle, then the 2 acute angles of a right triangle are complementary, right? If this is 90 here, then you're going to take the 90 away from the 180, then you're only going to have 90 left. So that means that measure of angle 1 plus 32 would get you to the 90. So that just, if you know that, right, that measure of angle 1 plus 32 gets you to 90, you can do this a lot faster. You can kind of do it in your head, right? If you're quick with, if you're one of your strengths is mental math, right? Numbers in your head. Okay, or you can just do it out, right? Subtract 32 from both sides, and then you're going to get 58. All right, we got parallel lines, so that's going to probably come up in this problem here. Is there anything we do with parallel lines? Well, not quite yet. Let's see. Oh, we have 32 here, and we have a parallel line there, a parallel line there. That's going to help us get 3, because 32 and angle 3 here, what kind of angles are those? What relationship is that? Alternate interior angles. Very nice. Okay, so this is 32 right here. And that helps us out. This is 35. So you just got to subtract that from 180. So 180 minus 35 minus 32. You're taking away, how much from this? You're taking away 35 minus 32 is 67. You're taking 67 away from 180. So that's 113, right? 4 would be 113. And then that's good here. So we have none of these, or do we, right? Do we? Oh, we have a straight angle right here. One of the 2 angles is 90 degrees. So then the other one's going to be 90 degrees right here. This adds to 180. Very good. So a straight angle here is just a line, right? And it's split by this 2 90-degree angles. So we know that it would take 180 away from 90, you get another 90-degree angle there. Okie doke. So now we have alternate interior angles. So angle 5 is 35 degrees. And that's just going to leave us with angle 6. Angle 6 is going to have to be the remainder of, right? So also, 2 acute angles of a right triangle, they sum to 90. So this is going to have to be 55 degrees, right? 55 plus 35 brings us to 90. Or 90 minus 35. Do that on a calculator real quick. Get 55. Good to go. Let's see if I have time here to get number 12 done. I think I do. 5% left of battery power. We got A, B, C, D, E is regular. Okay, so we have a regular they're telling you this for a reason, because you were practicing interior angles and exterior angles too, right, of a regular pentagon. And regular pentagon, you might just want to start. Why is it saying regular? Well, what comes to mind for me, because I've done problems like these, is that the interior angles are 108 degrees. Because, right, you got to know this formula, n minus 2 for a regular polygon, n minus 2 times 180. Well, for any convex polygon, that would be the total sum of interior angles. But then you divide that by n to figure out what one interior angle is equal to. So n minus 2 for a pentagon would be 5 minus 2, which is 3. And then 3 times 180, what is that? 540. Okay, 540. And 540 divided by 5, give that a calculator real quick. Just crunch the numbers. 540 divided by 5 would equal 108. So we know that the interior angles are 108. And we also know that the exterior angle, this is a good reminder here, that the exterior angle is just going to be what's left after we take 108 away from 180, right? Because the exterior angle's supplementary to the interior angle. So angle 2 here, we're going to get angle 2 as exterior angle, is going to be 72 degrees. Another way to do that is you can do 360 divided by n, right, to get an exterior angle. So this is an important formula to know as well. Just it's going to let you move faster in problems as we do more throughout the rest of the year. 360 divided by n. So 360 divided by 5 would equal 72. So that means 2 is 72. We got a 72 right here. It looks like that means these lines have got to be parallel to one another. Oh, nice. I like that. These are alternate interior angles and they're congruent, cut by transversal. These two lines are parallel. That's good. So these are corresponding angles. So those would have to be the same. Let's see here. Think. Mr. Fortin's actually got to think through this one a little bit here. This is 108. Okay, so we know that this whole thing, right? This whole thing right here is 108. And we know what's in blue is 72. So if we do 108 minus 72, that's going to tell us the measure of angle 5. So 108 minus 72, it's been a while since we've done subtraction like this. Oh geez, this is going to be 36. Forget how they really teach this to you guys here. So we got 36 for this angle. That means angle 3 is going to be 36. And angle 1 is going to be what's left over after we take 180, subtract 72 from it. That would be 108, and then subtract 36 from it. And that would also be 72. Okay, so this is 72 right here. Those are congruent. Interesting. Okay, so and then that brings us to angle 6 and angle 4. This is a little tricky here. Let me try to see. Well, this is 108. This is 108. This is going to have to be 72 as well, because this is going to have to add up. This is a quadrilateral in here. Look, EDCB is a quadrilateral. And what do we know about a quadrilateral's interior angles? Okay, we've already deduced that this angle is 108 and that angle is 108 because these are interior angles of the regular pentagon. And this was given to us, this is 72. So we know because a quadrilateral's interior angles, they sum to 360. So that means that this angle here that we didn't know originally, we would just take away the other angles from it. We had 72 degrees here, and then we knew that that's 108 and 108. So if we subtracted those from 360, we would get the angle measurement for angle DEB, which is 72, right? 72 as well. So we have 72 here, and then that means angle 6 is 108 minus 72, which is also going to be 36. And this is isosceles here, 36 and 36, and that adds to 72. So this is also going to be 108. This is also a interior angle of a regular pentagon here. So we have all the angle measurements here. You're going to have to look in, maybe zoom in real quick. Let's see. And hopefully you can read what I wrote so you can check your answers. Okay, trickier problem, but hey, I think that's probably a good level for an assessment or not. Number 13 in the diagram for exercise 12, explain why EB and DF must be parallel. I noticed that here. Notice I put this in here. I should have put it in red, but I was able to determine this because you remember when I did that? Oops. Yeah, sure, it's heading that way, and then I'll do heading this way here. So anyways, EB and CF, or DF, right? That's the line that contains CF here. Or the segment also contains segment DF. But they would have to be parallel to one another because I think we concluded this first, that angle, yeah, this was right here. Angle 2 had to equal 72 degrees. Angle, we knew this because angle EBF was given to us 72 degrees. And we determined that measure of angle BCF also equaled 72 degrees because it's an exterior angle of reg pentagon. So we could determine that angle EBF was congruent to angle BCF. Fits the definition of congruency for angles because their measurements are the same. So then at that point, if we're writing proof for this, right, we would know that we would the two lines had to be parallel because the reason would be if two lines, right, EB and DF, cut by transversal, and stuff happens with congruent angles, and they did, right? We determined that they did, and alternate interior angles are congruent, then lines are parallel. So this is sort of the main reason why we know that, but here's all our evidence leading up to that. So you probably want to write down all of that rationale so you can fully demonstrate why you know that EB and DF must be parallel. All right, going well, I think. Going well, but I've had practice on this. I've done this a bit in my day. Hopefully it's going okay with you. Again, if it's not the night before a quiz, then reach out to your teacher or ask a classmate for help if you're getting worried and it's getting close to the deadline here. Anyways, jumping on in stuff. Hopefully your teacher had a chance to go through this with you. It is interesting if you did the logic unit earlier in the semester. Some teachers do this before the semester began. Perhaps they didn't go through this with you in detail this time around, but it's a bit of a review. If not, let's follow along here because, hey, one thing you notice here with a lot of the theorems, note here that this is actually a true statement, right? If x equals y, then x squared would equal y squared, right? That would work for any real number, right? That would equal any real number. If any real number is the same or any expression is the same, you square it, the result is going to be a statement of equality. So equality is preserved here, right, under this condition. So anyways, let's get rid of that. But remember that, right, this whole if-then thing, that's something you're seeing a lot in geometry because that's the way that facts oftentimes are written. Facts are predicated on having an if hypothesis, right, which is, a fancy word for that is a premise, right? A premise is kind of like a situation. It's where we find ourselves. So the situation is, well, our given situation is this. If x equals y, that's our given situation. Then, right, a result, a consequence of that is that x squared would have to equal y squared. So given a hypothesis, right, where we start our situation, right, hypothesis of x equaling y, then our conclusion, right, we can conclude because we would know it would follow x squared would have to equal y squared. We can test that all about, and we can just assume that that's true. I think that is mostly an axiom or a postulate of algebra right there, but we know it's true because it's so obvious if we test it a whole bunch of times. Anyways, proof, I don't think there's a proof for that. It's more of an assumption, but we know it's true because that's the way that math works. Anyways, write the hypothesis, okay? So this is, if you did this, the logic unit earlier, this is kind of a lot easier because in the logic unit, you weren't writing it like this, if-then. You had a symbol for if-then. If-then symbol is actually in math is this, if-then. And that logic unit is a subset. It's called discrete math. So if you take discrete math classes in college, they might do stuff like this. This means if-then. So remember, if P, then Q. This stands for if P, then Q. Okay, so if P, then Q. And the P part is the hypothesis. The Q part is the conclusion, if it's written in the standard form right here. If P, then Q. So here you got if P, then Q. Okay, so if P, so if x equals y, then x squared equals y squared. So write the hypothesis. A is x equals y, and the conclusion, then, that's the part after the then, right? Hypothesis, conclusion, if then, and conclusion would be x squared equals y squared. And the converse of this, that's where this becomes really fun, okay? So remember, the converse is where you flip the hypothesis and flip the conclusion. So all of a sudden now, this is why using those symbols early in the year just helps you be more confident on this, is that all of a sudden you got if Q then P, right? The original conclusion, does that then lead towards, this is a consequence of knowing the original conclusion is true, that the original hypothesis, that would have to be true too. So that is called the converse statement here. Every statement has a converse statement. So if two lines cut by a transverse and alternate interior angles are congruent, then the lines are parallel, right? The converse of that would be we would move the conclusion to the hypothesis and vice versa. So here we just need to flip where this is. So let's move q to the front. So it's going to be if x squared equals y squared, then x equals y. Which, if you're thinking here, are like a question on a test that makes it a little bit harder because this is pretty easy so far. Question is the converse actually true? Think about it for a second. Don't get mixed up here. Don't go with your gut. Think through. Is this a true statement here? Is this always or sometimes or never true? This is only sometimes true. So if x squared equals y squared, yes, it's possible x equals y. So for instance, if x squared equaled 25 and y squared equals 25, it's possible that x would equal 5 and y would equal 5, right? That would all make sense. But if x squared equaled 25 and y squared equal 25, what's a value of if x were 5, for instance? It's a counterexample you have. What's an example of y that y could be that doesn't actually equal 5, doesn't equal x? Oh, right, -5. So this is actually a false converse, right? A false statement. So even though this was true, right, this is one of the founding postulates, I guess, of algebra, or an axiom. Its converse is not true. So, or it's only sometimes true. So we just say it's not true. Because why? This isn't a rule, right? We can't follow it all the time. Contrapositive. Oh yes, if this the original statement is true, then the contrapositive is always going to be true. That's going to be the one where, if you remember this from logic unit, if not, I'm showing it anyways. That's going to be the contrapositive is the one where you swing. When you see CO, that means kind of, hey, move the conclusion, right, to the hypothesis. You're going to do the same thing too. So contrapositive, kind of like the converse. So it's your converse, but it's the negation of the converse. So you would do the converse, Q, P, but if you did a logic unit, you might know these symbols. This means negation. This means not true, right? Not true. So here, not true, Q, right? If the original one is this, right? If P, then Q, of course. That's the original one. If P, then Q. Or if x, y, then x squared, y squared. So the contrapositive is let's move the x squared, y squared to the front, but let's make it negated. Let's negate it, and we'll also negate the original hypothesis, which has been moved to the conclusion because it's kind of like the converse. So what this means, the negation symbol means not or not true, right? Not, and we'll put not in front of it. Okay, so let's see who this gets reworded as here. So fx, well, we know it's not true. So if we know, actually, we didn't start with, I should put x squared. If x squared, right, because I got to start with the original conclusion. If x squared, I'm not going to make it not true. So if x squared doesn't equal y squared, then x, and I'm going to negate the original hypothesis, which is now the conclusion. Okay, so I'm doing not p. The original p was x equals y. So now not p is going to be at the conclusion, and we're going to do x equals y, but we're going to make it not true. X is not equal to y. And this is a true statement. Okay, this is a true statement. I'm going to put a little smiley face here, and I'm going to put a medium face here because it's not always true for the converse, but the contrapositive is always true if the original statement is true. Okay, it's always false if the original statement is false. So if this were false, we would know contrapositive is false because they're logically equivalent. So if x squared doesn't equal y squared, then we would know that x couldn't equal y, because if x squared were, for instance, 49 and y squared were 25, and there's no way that x could equal y, right? X could only be, like in that situation, positive or negative 7, and y can only be positive or negative 5. They're not going to equal each other. So that's the one thing, that's the one related statement that we know is always equivalent to the original statement, is the contrapositive. All right, let's check it out here. We don't have much left. We got a proof down here, and let's see if this gets a little bit harder than this. I wouldn't really say that these are completely advanced questions. So we got number 15 here. Use the statement if x equals y, then x squared equals y squared. Okay, so the same thing. Pair each statement below with the given statement above and tell what conclusion, if any, must follow. Okay, so we have here a given statement, and I'm going to rewrite this as given true premises, right? So this is premises, and again, just kind of means situation or known fact, and that we're going to accept, okay, that we're going to accept about the situation we found us in. Not all teachers have time for this section too, so it's possible this won't be on your test tomorrow, or assessment coming up pretty soon, or quiz if they call it quizzes like I do. Okay, so we're going to accept that x squared must equals y squared is true. Can we conclude anything else? Well, the original statement here was this, right? If x equals y, then we would know that x squared equals y squared, okay? So we know that x squared equals y squared. Is there a conclusion we can make about x equals y? Do we know that that's actually true? No, we don't, right? We don't know. This is just a question mark here. It's possible, right? If we know that x squared equals y squared, it's possible that they equal each other. It's also possible they're different, right? If x squared equals y squared and they're both 25, it's possible that x is 5 and y is negative 5, okay? So I'm going to put here, no conclusion possible here. So if you know that the conclusion of a theorem is true, you might know that the hypothesis might be true in that exact situation, but it might not have actually happened, right? You just, the sort of the difference between causing something and being necessary, right? Necessary and sufficient, which perhaps you studied earlier on. So the x equals y is sufficient to making x squared equals y squared be a known fact, but it is not necessary, right? There are other ways you can get x squared equaling y squared where the hypothesis isn't actually true. So yeah, no conclusion here. Okay, so same thing here, part B. Again, we'll write what we know as a fact. A given statement is this: x equals y. If x equals y, then x squared doesn't equal y squared. Oops, sorry, does equal y squared. You know that this is a true statement, okay? But whatever situation we're analyzing right here, we happen to know that x squared doesn't equal y squared. Any conclusion we can make, okay? So this here was sufficient to establish this being true, but this is not true, right? This is not true. So if this is not true, right, your conclusion is not true, we know that this didn't happen either, right? There's no way, if x squared doesn't equal y squared, our conclusion here is that x doesn't equal y. So if our conclusion didn't happen, right, if we know our conclusion didn't happen, then that means we know our hypothesis doesn't happen in this situation as well, okay, as well. So if we have an x here, we're going to have an x here. If this is true here, it's possible this is true, the hypothesis is true, but not for sure. Okay, so here, it's a lot easier when they give you stuff. So nice, they're going to start giving stuff by the hypothesis. The hypothesis is easy because it tells you if it's sufficient to making the conclusion true. So if x equals y, right, if we know that's true because that's given to us up here, then we're going to know the conclusion of this true statement above here must happen. We're going to know if we have given two numbers and they equal each other, then the squares of which would also equal each other. Okay, so we can conclude here, our conclusion to this is going to be that x squared would have to equal y squared. If we knew that the hypothesis of the statement is true, then all right, and finally, last one right here. Again, we'll write down the statement we're looking to read into. If we know that the hypothesis didn't happen, well, the hypothesis is sufficient to making the conclusion happen, right? If we know x equals y, then we would know, right, because it would make it sufficient that the conclusion were true. But is it necessary? Does x have to equal y? And that's the only way we can get from a specific premise to knowing that x squared equal y squared? No, there's other ways to get there. Okay, it's possible that if x didn't equal y, there are other ways, right? If, for instance, if y equaled the opposite of x, then we would also know that would be a way to get to the second statement true here. So if x doesn't equal y, right? If the hypothesis doesn't happen, we don't know if the conclusion happened at all, right? It's insufficient right here. So if it happens, it's sufficient to know if it's true. If the hypothesis, we don't know if it's true in the situation we're on here, then we're not going to know. We can't draw any conclusions because we have no theorem to apply there. So we're writing no conclusion possible. Okay, so to summarize these four different scenarios, if we know that the conclusion happens, that's not going to tell us anything about whether the hypothesis is happening in our situation. And then if we know that the hypothesis didn't happen, then we're not going to know if the conclusion happened, okay? Whereas here, it's a little bit more certain. If the conclusion didn't happen, then that means the hypothesis, right, which would cause the conclusion to happen, that means that didn't happen either, okay? And finally, if the hypothesis happens, right, we have a theorem, we have an assumption that we know is true, then we're going to know the conclusion of that assumption must have happened in that situation. Okay, so try to navigate those. There's really just stuff you have to reason through and think about. But you can kind of perhaps memorize at least a little bit of these scenarios to hopefully get there. Okie dokie, last one here. Everybody's favorite 5-letter word. Is it 5 letters or is it 6? No, it's 5. Yes, P-roof. Proof. Okay. And we have this here. So yeah, I have this lined up. Hey, when you get to this on an assessment or whatever, just get it set up. Set it up here. Real quick, just tell me statements, reasons, stay organized. Boom, you can jump into it. You don't have to think about it. So a proof has given premises. It has a proof statement you're working to get through. And then you got your chain of reasoning down here. But don't forget, you also have this diagram. So early on in the year, I really, really try to stress this because, hey, you're just trying to pick up any big wins, any quick wins, easy wins you have possible. And that's when you have something like this. Read through your given premises. It's going to tell you what you know about this diagram. And then show what you know in the diagram, mark it up, because then you're going to see how things connect and hopefully get a little more illuminated into like how I can actually connect this, right? These given premises, how I can get this to follow from it. If AB is parallel to CD and BF bisects ABE and ray DG bisects angle CDB, then, right, BF must be parallel to DG, right? That's a theorem, a very specific theorem that you're trying to prove right now, okay? So mark it up, take a deep breath, mark it up. AB is parallel, they marked this up for you already. So AB is parallel to CD, that's nice. We're gonna be able to prove a lot of angles are congruent to one another, might get to that later. And BF bisects angle ABE. So we're gonna have to say this in the theorem at some point, but I'm gonna mark it up so we don't forget to say it, that we have an angle bisector here. So that means that ray BF, okay, BF here is going to have to, this ray here is an angle bisector. It's going to have to create 2 congruent angles. So I'm going to mark this up here because that's probably going to come up in the proof. DG, ray DG bisects angle CDB. So that's another one where we're going to know this is congruent to this. And then we might as well mark up what we're trying to prove. We're trying to prove that BF, where is BF? Right here. Is it parallel to this? Okay, so maybe you think for a second and you try to work backwards. This is what we're trying to prove, this here and this here. And you think about what are some ways we can connect to it here? Like, well, I think if we can get some of these angles related to this line, congruent to some of the angles formed with this line, and we do that with any of these transversals, transversal here, if we can get those angles congruent, then I think we'd be able to prove that these 2 lines were parallel to one another. Right? That's sort of my game plan for this one, okay? So we have this marked up, and I should have put that 2 tick marks down here because these 2 angles are congruent to one another, and we're given parallel lines, okay? So we have parallel lines here. So now we're looking and we're thinking, what are some ways we can connect this line to this line right here, okay? Well, if we know that this angle is congruent to that angle, that would get these 2 lines parallel to one another, but we don't. We don't know that that angle is congruent to that angle. Let's see here. Let's get this angle. Well, we know that that angle actually would have to be congruent to this angle because it's given. Okay, it's given here that this angle is congruent to that angle. That could help us potentially. What else do we know? Well, that angle is also congruent to that angle because, they're vertical angles. And those are congruent. Okay, that might be helpful here. This is actually kind of a trickier one than I was expecting. I'm drawing it up, and so now I'm thinking. So after looking at it for a minute, I think I got it here, but let's go ahead and write in our given information because you need this for the proof. So step 2, we're going to use what we're given here that we used to mark up the diagrams right here. So you're writing stuff down, and even where you don't know where to go from here, even maybe just writing it down might make it easier to be like, how do I get these angles really to connect to these angles? Because when you have statements of congruency here, eventually we want to get congruency related to maybe these 2 angles here. And the way I'm seeing this is my goal is to maybe get this angle congruent to this angle right here. And And if I do, actually, wait a second, these two angles would need to be congruent. So maybe these connect somehow. So I want to do this in step 3 at least a little bit. Might be a little confusing that I'm doing this step 3, but I want to get this out of the way. Angle FBE, that is, angle FB, that's congruent to angle DB, and we don't actually have a point here, so maybe there's an easier way to do this that I haven't figured out. So I'm going to put Z here, DBZ, and that's because vertical angles are congruent. And that's going to help me because I've actually spied a way I can get these angles related to these angles here. I know that these are congruent to one another, so they're definitely related. But these angles here and these angles are here. How are they related? How are they related? Oh, that's right. It's given to us. This is where having marked up, we know that this is true and that is true. So we know that this angle is congruent to this angle down here. Because what's the relationship between those two angles, right? We have two parallel lines cut by a transversal right here, and what's these kind of larger obtuse angle looking angles here? What's their relationship on there? Oh, they're congruent to one another because they are corresponding angles, and that'll be my next step. All right, so I got those congruent to one another. That's gonna mean that I can eventually prove this through a couple more steps, right? I got larger angles congruent here, and then I know that I got two angles that are gonna sum to be this, and two angles that are summed to be this, and right, they're congruent to one another, congruent to another. So this eventually, right, I'll be able to say EBF congruent to angle BDG, and that's gonna help me get to this angle congruent to that angle. Anyways, that comes later. And the way that we do that is because of the angle bisector theorem, that we can actually say that twice the measure of angle CGDB equals the measure of angle BDC, and twice the measure of angle EBF. Got my dog barking in the background here. Geometry wasn't hard enough to begin with. You got dogs barking in the background. Twice the measure of this angle up here would have to equal double the part here equals the whole, because that's an angle bisector. We get measure of angle EBA. And that's the angle bisector theorem. And this is going to get us close, right? We know that because measure of angle EBA is equal to measure of angle BDC, which we have in step 4. We're going to be able to set these two expressions equal to each other. And that's going to be good because that's going to help us get us a proof in here, right? We know that measure of angle BDC equals measure of angle EBA because they're congruent angles. They're congruent to one another. So here, what we can do is we can take this, and maybe I'll change this to the measure of an angle here and measure of an angle here. We can take this, because this equals measure of angle BDC, we can replace it in here, right? We can substitute it in here. We can take this expression, it equals this expression. We can substitute it in here. So here, when you have 4 kind of expressions, and 2 equal each other, and then one of those equals something else, and one of those equals something else. When you have 4 expressions like this kind of moving interchangeably, that's the substitution property of equality, right? I changed the congruency to equality here. So I'm going to write that in, that 2 measure of angle CDB equals 2 times by the measure of angle EBF. Step 7 is going to get us to saying that measure of angle CDB equals measure of angle EBF, and we know that's true because we just divided both sides by 2. So that's the division property of equality. So now we have proven that this no longer needs 2 tick marks. It just needs 1 tick mark because it's congruent to angle EBF, right? Measure BDA is congruent, or CDB. Yes, what did I do here? CDB. No. 2 times measure of angle G. It's G right there. Yeah, G. So GDB, this angle right here, is equal to the measure of angle EBF, right? EBF. And I didn't put the F there. So we know that those 2 angles are congruent. And earlier we said that these 2 angles are congruent. Okay, so this angle congruent to that angle, and that angle congruent to that angle. So now we have 3 angles. right? And we're sharing congruency impossible. We have a common angle that's congruent to that angle and congruent to that angle. So if this angle is congruent to that angle, and that angle is congruent to that angle, we're talking about the transitive property here. When two things, this angle and this angle, both congruent to the same angle, then they are congruent to each other. That's the one that's tricky here. So you get substitution on this one, and you get transitive on this one. The classic, is it substitution, is it transitive? I don't know. But we said this earlier here. Earlier in the proof, we said that, this is where any vertical angles are congruent, are important to my proof at least, that angle FBE, this right here, FBE, is congruent to DBZ, which is right here. Now I want to say that measure of angle DBZ is equal to measure of angle GDB. And I know this because of transitivity, transitive property. Pesky, but you'll learn it, you'll get there, okay? And I know that because DBZ equals FBE, and FBE right here, this is FBE right here, right? FBE or EBF, that also equals GDB, right? GDB right here equals EBF, okay? So now we have EBF, right? This is the common thread between the two. We have this one expression is equal to two different expressions. So that two different expressions must be equal to each other. And again, usually you put your measurement symbols here, and let's just get rid of the congruency. I'm going to do measure of and then equal to, just for the sake of it looking alike. Okay, so messy, but I'm getting there. Okay, so now I have this angle right here. Whew, congruent to this angle right here. I'm just showing it new ones, and I'll just do 4 tick marks, I guess. And that's important. Oh, wait, no, this isn't the one I care about. I cared about this here. 1, 2, 3, 4. So messy, but I'm not going to refilm this video because math is messy sometimes. And there's probably a faster way to do this because they didn't even mark, give a coordinate right here. It's probably an easier way to do it. But anyway, maybe I'll hop back on the assignment to talk about an easier way to do it later. You just tell me, right in class, Mr. Fortin, this is the way that we do this. But now we know that this is going to be this line parallel to that line because these are alternate interior angles, and we proved they're congruent to one another. So because we know this, right, that's going to get us to what we're looking to prove, which is that BF is parallel to DG. And we know that because if two parallel lines, if two lines cut by a transversal and alt int angles congruent, then we've established the lines must be parallel. So that's my 9-step proof. Let me zoom out so maybe you can see the whole thing and we can look at the diagram. Was there an easier way to get there? I just noticed here that the Z thing, right? I've noticed it a long time ago that the Z wasn't actually marked. So I added a point there. I just labeled the vertex so I could talk about it in the proof. Probably you talked about this, right? So if you did this faster, like Mr. Fortin, there's a faster way. You probably talked about stuff over here because they're labeling. They're giving you all these points here. They're giving you A, they're giving you G, right? So, they're parallel. So maybe you could have said that these were congruent to that. Does that help? I don't know. I don't know if there's an easier way. Tell me. Send me an email. Tell me if there's an easier way. Okay? So that's that. That's the chapter test, number 1 through 16. Hopefully things went well, and reach out if you have any questions. Take care. Bye.